Hello viewers, welcome back to my channel. We're still moving on with our second topic, that is the thin lenses. Okay, so my name is Dr. DORCAS NGIGI. I welcome you so that we continue together. Now, in the last lesson, we looked at graphical analysis of the lens formula. We looked at graphical analysis of the lens formula, how we can use that lens formula to, we can determine the focal length of a lens from experiments. Okay, so one of the experiments is by varying the object distance and the corresponding image distance. And from the information that we get, then we plot a graph. Okay, and we can plot different types of graphs. And from those different types of graphs, we looked at two, we can be able to determine the focal length. So we're going to continue on the same. So if we have I'm using a converging lens. So now we're good at that, which has F to F, has F to F. So if we put an object anywhere along the principal axis, as long as it is not between F and the optical center, then we will be getting true images. When the object is at infinity or behind the center of curvature to F, or between 2F and F, the image will form on the other side of the lens and it will be a true image. So from the rules that we followed, that ray which is parallel and close to the principal axis should be refracted through the principal focus, and the one that is passing through the optical center, that one should pass undeviated. So this is just an example of that. So we called the distance from the object to the optical center, we called it as the object, that's the image. We call that distance U. And the distance from the optical center to the image, we call that distance V. Okay? And therefore, we can vary U. That is, by bringing the object closer to the lens or by moving it away from the lens, we vary U. And by varying U, then automatically the V will also vary. Remember, as you bring the object closer to the principal axis, the image moves further away from, as you bring the object closer to the lens, the image moves further away from the lens. So every U will have its corresponding V. And from that information, now we can put that information on a graph, where we said we can have U in centimeters and V, corresponding V in centimeters. And we said we can have different values. So let's say U1, U2, U3, U4, U5, and corresponding image distances, that is V1, V2, V3, V4, and V5. Okay. Now, this information, we created other columns where one was for 1 over V, 1 over U per centimeter, so 1 over U1, 1 over U2, 1 over U3, 1 over U4, 1 over U5, and of course 1 over V per centimeter, where you have 1 over V1, 1 over V2, 1 over V3, 1 over V4, and 1 over V5. The other column we created was magnification, which is U in centimeters divided by V in centimeters divided by U in centimeters. That is simply magnification, which is V in centimeter over U in centimeter. So of course, if we take V1 over U1, we are going to have magnification 1, M1, M2, M3, M4, and M5. And from that information, we were able to plot two graphs. So this is the experiment that you are supposed to carry out. And those are the values that you record of U and V. And from U and V, then you can record the rest. Okay? So we plotted two graphs. One graph was 1 over U, 1 over V against 1 over U. And from that, we were able to get the focal length. I want you to go back to the previous video and check how we did that. The other graph we plotted was for magnification M against V, which again helped us to get the helped us to get the focal length. Again, it is in the previous video. Go again and check how we plotted that graph. Now, from this information, still there's something else we can do. We can get a graph. We can create extra columns. One column of V plus U. And another column, this simply image. I don't want you to get confused. You can put it inside there. And another for VU. Okay, those are two columns. So how do I fill this? This is V1 plus U1. This is V2 plus U2. V3 plus U3. V4 plus U4. And V5 plus U5. Okay, these are V plus U. The other one is UV. Okay, so now this is what? This is centimeter square. Remember, it's centimeter times centimeter. And U plus V, that one is in centimeters. Okay, so this is V1 U1, V2 U2, V3 U3, V4 U4, and V5 U5. Okay, now that we are getting from the same experiment, because all of them are coming from U and V. V plus U, UV, or whether it's V over M to get magnification, all of them we are getting from U and V. Okay? Now, the mirror formula, let's go back. The mirror formula 1 over F equals to 1 over U plus 1 over V. Okay? So, we have added two columns, V plus U and UV. So we need to get them from this equation. Now to get that, let's take the LCM of U and V. The LCM of U and V is U times V, which is UV. Okay, so that is UV. Okay, now U goes to UV how many times? It's like saying UV divided by U. So it goes U goes to UV V times. It's the same as UV divided by U. So UV divided by U gives us V. So U goes to UV V times. So V times 1, that is V. Plus V goes to UV how many times? It goes to UV U times. It's the same as UV divided by U. It's like UV divided by V. So V and V cancel, we are left with U. So V goes to UV U times. U times 1 is U. Okay? So what are we having? We are having 1 over F equals to V plus U over UV. Okay? But now, what about, I want to make V plus U the subject. Or better yet, we make UV the subject. I'm going to show you why. So make UV the subject by multiplying by UV both sides. So UV will be equal to, multiply by F both sides, will be equal to F into V plus U. I've just rearranged that equation so that I make UV the subject. So UV is equal to F into V plus U. Now you see where we're coming from. UV is this, and V plus U is V plus U, is that column. Okay, now if we get this to the equation of a straight line, so what we have, straight line is Y equals to straight line is y is equals to mx plus c. Now, by now you are familiar with how we are relating the two equations. We did that in the last two graphs that we did. Okay, so our uv is our y, our v plus u is our x. Remember, uv is a variable, v plus u is also a variable. As long as v is varying and u is varying, then v plus u will also be a variable. But f is a constant. Here we have y is variable, x is a variable, but m is a constant, which is the gradient of the straight line. So if we equate them, then uv is our y, v plus u is our x, then automatically our gradient will be f. That is for a graph of uv against v plus u. Please don't get confused. Then what about c, the y-intercept? The y-intercept will be equal to, if I add, there's nothing here. But saying there's nothing does not mean that there's nothing. What? There is something, but that thing is 0. Okay? Is 0. So that now, the intercept where the straight line cuts the UV axis is at the origin 0, 0. So it is there, but it is 0. So C is 0, M is F, X is V plus U, and Y is UV. Okay, so if I plot a graph, of UV, this one, to avoid confusion, this V times U is the same as U times V, there's no difference. Okay, so against 1 V plus U, then what do I get? 1, I get a straight line, because this equation and this equation are equivalent. Number 2, my gradient F is positive. As you can see, there is no negative here, so it's a positive gradient. So that line is like that. Number 3, where the line cuts my UV axis is at 0. The y-intercept is 0, so I expect my straight line to cut my graph at that point. So I can as well draw that. That is the graph of UV against V plus U. Okay, so the gradient of this, so this is our y-intercept, 0 is our C. 0, 0, because it's not there, that's why it was not there, because it's 0. So it cuts the graph at the origin 0, 0. Okay, then the gradient, change in UV against change in V plus U, our gradient, which is change in UV against change in V plus U, that should give us F. Okay, so the gradient of our graph is the focal length. The gradient of a graph of UV against V plus U is the focal length of our length. So we have been able to analyze the length formula. 1 over F is equals to 1 over U plus 1 over V. And from it, we have been able to plot 3 different graphs. And from all those 3 different graphs, we have been able to calculate or to determine the focal length of our length. Because this experiment, the purpose of this experiment is to determine the focal length. Okay? So we're going to look at something else. Still, we are using our length formula we are analyzing our length formula, and we are using it to determine the focal length of our lens. We're still using the length formula, and we are using it to determine the focal length of a lens. Now there's a method we call displacement. We call it the displacement method. So we want to determine the focal length using what we call the displacement method. Now, to understand the displacement method, let me draw back my lens. So there are 2 points which we can place our object. We can place our object behind C from the lens to where we have the object, where the object is behind the center of curvature. This is our object. And where do we form the image? Now, if the object is behind the center of curvature, then the image should form somewhere there between F and the center of curvature to F. Now, what are the image characteristics? It's true. It is inverted. It forms between F and 2F, and it is smaller than the object. Okay? So if I call this object 1, and that I call image 1, then if I move the object closer to the lens so that it falls between 2F and F, the same object, same height. So we are using the same object. Calling it object 2 does not mean I've changed the object. It's still the same object, but in 2 different positions. Okay. So if we do that, now the image this time will be behind C, and what will be the characteristics? It will be true. It will be inverted, but this time it will be magnified. Then we call that image 2. Okay. Now with that, if we remember the principle of reversibility of light, if the object is behind C, the image is between F and C. And if the object is between F and C, the image is behind C. Okay? And as the object moves closer to the lens, the image moves further away from the lens, and it becomes bigger and bigger. It becomes magnified. Now, this is the principle of the displacement method. We move the lens, the object, from one point to another point, so that the image shifts from this point to this point. Now, if we measure this distance here, and that distance there, we find that the 2 distances are equal. So in displacement method, that is what we do. Now, we have the object. Let's say I have a cross wire there as my object, and I'm going to light it. So I put something like a bulb, the source of light. What for? I want to illuminate my object. Then I put a screen. The screen. Okay, so with that, I have an object. I have my lens. So the distance, I measure the distance from that point to that point. Let me call that distance S. Okay. Then let me come with my lens. So that is my converging lens. And let me call this point L1. Now, what is L1? Now, the distance from my lens to my object, let's call it U1. Okay? U1. And that U1 is the object distance. Then, when my object is here, the image will fall on the screen. Now, the image will fall on the screen, but what will be this image? Now, I'm putting this object in such a way that it is falling between F and 2F of my lens. So F is here, 2F is somewhere here. So my object is between F and 2F. So where will my image form? The screen is behind C, is behind the center of curvature. So how do I expect the image to be? It will be very large on the screen. It will be magnified. Okay? Then I will call that image distance V. Okay? Now I change the position of my lens. I change the position of my lens so that now it changes position maybe to somewhere here. So it's the same lens. So the lens has shifted position from point 1 to point 2. The same lens. But why have I shifted now my lens? Because now I want my object to fall behind C. So when the lens is here, its F is here, its 2F is somewhere here. So the object this time is behind C. And when the object is behind C, where does the image form? The image forms between F and C. So this is F and that is C somewhere behind the screen. And so the image is forming between F and C. What are the characteristics? Now the image will be smaller than the object, but it will be true and inverted. So when we fix that distance S, we are going to have two images on our screen. We are not moving the screen and we are not moving the object. We are only moving the lens. And when we move the lens, we are going to form two images. One magnified image and one image that is diminished. Now we measure the second object distance from the lens to the object. That is our U2. And the image distance is from the lens to the screen. That is our V2. Okay? I hope you're getting that. So what is this? So what has happened? So I've just shifted the lens and my object distance has changed automatically, and automatically the image distance will also change. But this distance from the lens, from the object to the screen, that distance I've maintained, and that is the distance I'm calling S. So I can as well say that S equals to U plus V. Okay? It is U plus V. Whether it is U1 plus V1 or it's U2 plus V2, it is U plus V. Okay, now there's another length I want us to determine. Our object was at L1 and now it is at L2. So we have shifted it. What is this distance from where L1 was to where L2 was? Now to understand that, we need to look at these two. The principle of reversibility of light. U2 should be equal to V1 and V2 should be equal to U1. This distance is equal to this, and this distance here is equal to that. And if that is the case, then if you take a good look, then you realize that D is always V minus U, meaning the distance from here to here, if I subtract the distance from here to here, which is equal to from here to here, remember we have said U1 equals to V2. U1 equals to V2. So this distance here, that is V1, minus this distance here, which is V2, which we are saying is equal to U1. So this the V1 minus U1 is D. So D is simply V minus U. Okay? I go back. V2 is equal to U1 and U2 is equal to V1, the principle of reversibility of light. If understanding that, then what is D? D is the distance between the first position of the lens and the second position of the lens. So that is D. How do I get D? The whole of that is S. From here to here is V1. Now to get D is from here to here. So to get D, I must take that distance minus that distance. So it is V1 minus V2. But what is V2? V2 is U1. So it is V1 minus U1. Okay? So it is simply V minus U. Okay, so I think I have to delete this, be able to work out. So what do we have? We have S as U1 plus V1, and we have D as V1 minus U1. Okay? So let's add S plus D equals to, that is the same as U1 plus V1, add v1 minus u1. So I'm just taking s and adding to d. So s plus d is that plus that, okay? So which is u1 plus v1, open the brackets, plus v1 plus minus, that is minus u1. Don't get lost. So what do we have? u1 minus u1, those one cancel. So we have s plus d equals to v1 plus v1, that is 2v. 2v1, of course, okay? So what do we have? Making v1 the subject, then we have v1 is the same as s plus d over 2. Okay? Now what about s minus d? What does it give us? So s minus d, that is u1 plus v1, u1 plus v1 minus, we are subtracting now, s minus d, v1 minus u1. Okay, open the bracket, u1 plus v1 minus v1 plus minus minus, that is plus u1. Okay, now what do we have? Plus v1 minus v1, so it's the same as v1 minus v1, that is 0, that's one cancel. Then u1 plus u1, that is 2u1. So s minus d equals to 2u1. So finally, what is u1? u1 equals to s minus d over 2. So where are we looking at this? Let's now invoke the mirror lens formula. So what does it say? It says that 1 over f equals to 1 over v plus 1 over u. Don't forget the lens formula. So 1 over f is therefore equal to 1 over v1, 1 over v1, which is s plus d over 2, plus 1 over u1. What is u1? S minus d over 2. Now, whether you used u1 and v1 or you used v2 and u2, the results will be the same. So I leave you that for your own practice. So from there, what does it give us here? So this is the same, 1 divided by s plus d over 2 is the same as 1 times reciprocal, that is 1 times 2 over s plus d, that is 2 over s plus d, plus, same here, it is 2 over s minus d. What am I saying here? 1 divided by s plus d over 2, every whole number is over 1, is the same as 1 over 1 times reciprocal of this, 2 over s plus d, which is the same as 1 times 2 is 2, 1 times that is s plus d. So don't get confused. Okay, so we have 1 over f equals to what? Now, look at this. LCM is s plus d into s minus d. So s plus d goes to this. How many times? That cancels with this. So it goes to there s minus d times. So it is 2 into s minus d plus 2. This goes cancels with that. Gives us this to s plus d. Okay, open the brackets. That is 2s minus 2d plus 2s plus 2d. 2s minus 2d plus 2s plus 2d. So minus 2d plus 2d cancels, divided by, now s plus d, s minus d. Now you have done that in mathematics. A plus b into a minus b is the same as a squared minus b squared. So if we apply that here, if you want, you can do the long, open the bracket the long way, then you will still get the same. Okay, so this is the same as s squared minus d squared. So these have cancelled. So what we have 1 over f equals 2s plus 2s, that is 4s, divided by s squared minus d squared. Now, we are not interested in 1 over d. We are interested in d. So to get d, what do we get? F over 1 will be equal to s squared minus d squared over 4s. And this is what we are interested in. That's what we are interested in. And we have gotten that from the displacement method. So which we have said, we simply measure the distance from the object to the screen. We call that distance s, which is object distance plus image distance. Now the other thing, we vary the lengths so that now we form two different types of images. One magnified image when the object x is between f and 2f. We get a magnified image on the screen behind the 2f of our lens. The other image we form is a small image diminished, and when we form that, as we move the lens far away from the object, then this object falls behind C of our lens, okay? And so the image on the other side will form between f and 2f, and what will be the characteristics? The image will be much smaller than the object. It will be diminished. Now the distance from the first position of the lens and the second position of the lens, that is what we call D. And when we look at it from the principle of reversibility of light, then that is the image distance minus the object distance, okay? Yeah, now I've followed that. So I've said V2 is V1 and V2 is U1 from the principle of reversibility of light. Now with that information, now we have just put everything in place, S plus D, which has given us that we have followed that, got V1 is S plus D over 2, S minus D, we have followed that to U1, U1 is S minus D over 2. Now finally, now we use the mirror formula, the lens formula, 1 over F is 1 over V plus 1 over U. And now that is our V and that is our U. So when you just apply it directly as it is, 1 over U plus 1 over V. And when we apply it, we end up with 1 over F is 4S plus S squared minus D squared. And finally, F, the reciprocal is the reciprocal of that, which is S squared minus D squared over S. Now when you look at that principle of focal length, we don't need to know the focal length of the lens when you are doing the experiment. We just fix S and get the corresponding D. And with S and D, we are able to calculate the focal length of our lens. Now that brings us to the end of using the lens formula, graphical analysis of our lens formula. We can put that information on a graph. If you want, you can put this information on a graph where easily you multiply by 4s, so we get 4s will be equal to f into s squared minus d squared, okay? So if you plot a graph of, let me do it here, we plot a graph of 4s against s squared minus d squared, what do you get? You get a straight line through the origin. As you can see, it's plus 0, so through the origin. And what will be your gradient? Your gradient, that is change in 4s over change in s squared minus d squared. That gradient will be your focal length. So you can still put it in graphical form, where you plot a graph of 4s against s squared minus d squared. And when you do that, then you get the focal length of your lens. So we have analyzed the lens formula, and we have looked at two different experiments that you can do. This one and the other one for varying the object distance to get the corresponding image distance. That brings us to the end of our lesson. I hope you enjoyed the lesson, and I'm hoping to see you in my next video. Don't forget to like and subscribe. For now, goodbye.